Yeah, share session 3 again. Possible. And 3, one more. 10 o'clock. Okay, session 3, yeah, please. Okay. Okay, Assalamualaikum. Very good morning to all. So before we start lecture, anything that you want to ask or raise up? Any issue? Any problem so far?
No, doctor.
Everything okay, yeah?
Alhamdulillah, okay.
Alhamdulillah, good. Okay, so today I would like to continue our lecture on the uh, what is it? Good morning, doctor. I still cannot scan the QR for the attendance. Try again. Try again. What session you?
I'm from section 4, doctor.
Okay, wait.
But yeah, I think I came to take your signature yesterday. I meet you in the office, so I
All right.
think the course is not fully properly registered in the system. So the QR
Okay.
code doesn't record
Yeah,
my.
no problem. Session 4. Okay, Hari, I want to share the material now, please. Sign up. Okay, I go back to session 4 for the last slide today. Later on, I will share again a minute. Session 4. Okay. Okay. Again, session 4. All right, so today I'm going to talk on the energy conversion process, how we convert electrical energy to mechanical energy and so on. So the process, how to get that, we will do this morning. So today I need to record this one first. Got this one. All right, it's recording already. Okay, I'm using the PDF file here because easy for me to whatever sketch here. So, how to move this one. The problem with the online. It's gone already. Right. Okay, 1.4 energy conversion process. So in this chapter, we focus more on the how we can convert the electrical energy to mechanical energy and otherwise, and vice versa. So what I mean by the electromechanical energy conversion? So we use the magnetic field actually to convert the electrical energy to mechanical energy and mechanical energy to electrical energy. So we use the magnetic energy in between or it's like the buffer between them. You cannot directly convert electrical to mechanical without using the magnetic energy. So we use the magnetic to convert electrical, mechanical, and other way around. So in terms of definition here, what is meaning by electromechanical energy conversion device? It's a device that have capability to convert electrical energy into mechanical energy or converts mechanical energy into electrical energy. So any device that this capability, we call it the electromechanical energy device. Such like the generator and motor and so on. So this device can convert both energy or both energy is easily lah. And then also, I don't want to share this one later on. Okay. So in this device, in this electrical mechanical energy device we can divide by three categories lah. Three categories. The first one we call it transducer. Transducer normally used for the measurement and control, or involve the small motion only lah. It's not a short motion or small motion. So basically, it can transform a signal of different form. For example, microphone, sensor, and speakers, and so on. So this kind of device also we call it the electromechanical device. For example, microphone convert from the sound to electrical energy, or something like that. Speaker, if convert electrical energy to the sound and so on. So this kind of device we call it transducer. This the first category of the electromechanical device. The second one we call it the force producing device. This one normally involve the translational force with the limited mechanical motion. For example, actuators. So in the actuator, we can have relays, solenoid, and electromagnet. So this kind of device also, we call it the electromechanical device. It involves limited mechanical motion. It's not wide, but very limited motion. And the third one is we call it the continuous energy conversion equipment. Continuously, energy conversion can happen continuously, not for short period, but continuously. For example, in the motor or in the generator. Okay, so this kind of device that we see later on. So the next slide. So before we go to the process, we need to understand the principle of conservation of energy, where energy can neither be created or nor destroyed. It can only be changed from one form to another form only, and therefore total energy in the system is constant. This is a principle of the conservation of energy. So you cannot destroy energy, you cannot create energy, but you only can change the form of energy only. For example, electrical to mechanical, mechanical electrical, sound to electrical, and so on. There is a process or the principle of energy conservation works. Okay, for example, we have some device there. A loudspeaker, for example, is a kind of energy converter also. It convert electrical energy to sound energy. This kind of electromechanical device. And a lamp, for example, also can change the electrical energy to light energy. It convert electrical to light. And kettle, for example, is able to convert electrical energy to heat energy. This kind of energy conversion process You can change the form energy, but you cannot destroy it. Okay, what electrical energy? Basically, electrical energy. We have some more. First, we can transfer for long distance. It's good for electrical energy. I mean, for example, we have energy. We generate energy. We create energy, or we have power plant, for example, in Johor Bahru, electrical energy. So we want to transmit to this energy in form or electrical. We want to transmit to somewhere, Kuala Lumpur, whatever, far distance. So the best energy that can be transferred is electrical energy using the what the grid system and cable and so on. So that's why electric energy very important. You can transmit easily for long distance with less losses, for example. And the second part is why it's very important. You can transform electric energy to so many other forms using specific device. For example, you can use loudspeaker. And just now, you can change electrical to sound, and so on. That is a good thing about electrical energy, where this energy can be transferred to other form easily compared to other energy lah. So that's why we prefer electrical energy to transfer to other form. All right. So in electromechanical device, when we talk about electromechanical device, the system consists of three main parts, three essential parts. During the process it was three essential parts or three main parts. First, we must have electrical system. That means we need to electrical wires, electrical source and winding. This is the first one. The second part involve the magnetic circuit, which include the magnetic field in the magnetic core and air gaps normally. The third one is mechanical system. Where in mechanical system we can have mobile part, such as we have the rotor electrical system, or we have plunger in the relay. Okay. So these three main elements involved in any electromechanical energy conversion. Remember, so 1, 2, 3, electrical energy, magnetic energy, and also the third one is mechanical energy. So we can do some analogy based on this statement. For example, this analogy right? So we have water tap there here. So before this water here transfer to the other water tap, then we need to store first. Okay, something like that. So this one you call it electrical energy we electrical, and then need to store but in term of energy magnetic field before we can get mechanical energy. So this is like buffer. So conversion before we can change to electrical to mechanical, we need to store first the energy, converted to magnetic, then we can get mechanical energy. Or you can do like that This is your piping system, similar like this. Right. Okay, this water coming, which is electrical energy, and then we have storage water tank there, represent the magnetic energy. We store the water first before when you open the tap there, you got the mechanical energy output there. This analogy to show the relationship between mechanical energy here and electrical energy here. So during the process, there are some losses, or we have losses in electrical circuit, we have losses in magnetic, and also mechanical. Mechanical means losses in windage, friction, bearing. This is called mechanical losses. Magnetic means core in loss. We studied before, where we have losses in the eddy current and hysteresis that make the magnetic core hot and so on. And electrical system loss in the wires. When the current flow in the wires, we got I square R. So that means represent the losses. The power input that one must be minus losses first before you got the net power supply to the magnetic circuit. Practically there but ideally we can neglect the losses. Practically yes, there's always losses in the system. Okay, so now we can see we can represent the process of energy conversion by this one this modeling There are many representation that can be shared but here it's like a concept of electromechanical system modeling. So you got electromechanical system there. So it involves three parts, three main parts, which is electrical system, and then we got the magnetic system and also mechanical system. Depend on the system if the motor, for example, the input is electrical and the output is mechanical system for the motor. For the generator, for example, the input is mechanical and the output is electrical system. In between, you got magnetic system there, or magnetic store energy. Alright, I think this is very simple model to be understand. Okay. In electrical system, we need to understand voltage and current, and this one involve the Kirchhoff law, circuit, solution of circuit using Kirchhoff, KVL, KCL, Ohm's law, everything involved here. Okay, the magnetic circuit involve the magnetic flux, magnetic strength, magnetic intensity, and so on Okay, and then we have here mechanical system normally involve the speed, position, and acceleration, where sometimes we use the loss to solve a problem. So roughly the model is like that lah, for to represent the electromechanical system. Remember, we have magnetic, electrical, and also mechanical system. All right, this is same thing only. This next slide also just same phenomena, just to show, to make we more understanding about the system. Okay, we can put in the block diagram like that to represent the electromechanical energy process. So here you got electrical system, for example, is input. Then when we supply this input to the mechanical system through the magnetic system here, you got electrical loss just now. You got electrical loss. Then the energy stored in the magnetic system, you got field loss or magnetic loss, and then this one used to drive or to trigger the mechanical system. Then we got output mechanical here, net mechanical output. Then you got losses also in the mechanical system. Same thing lah. See, this on the flow of energy like that lah. This I think we can use for the motor. Motor, because input is electrical system. If mechanical generator is different way lah. Dia punya movement of arrow ni is different way. I mean they are from here to from the right to the left. Okay, simple lah. You got three system: electrical system, mechanical system, and also magnetic system. So we can write down the energy transfer equation as follow lah. So that means electrical energy from the source here equal to mechanical energy plus energy stored in the magnetic field plus energy loss. There is a energy balance equation, I call it energy balance equation. So this only the statement only, not that difficult to understand. Or the next slide also the same thing. For more detail lah, electric energy from source ni minus what? Losses, resistance loss. Okay, so this one we neglect lah. We just bring losses ni embedded to here already. Here we just make it total lah, but we can also represent it by electrical energy from source minus resistance loss equal to mechanical energy output plus friction and windage loss for the mechanical part plus increase in stored energy or decrease in stored energy plus core loss. Okay, depending on system, I mean you energize, you can say, you say increase. If you say de-energize, I mean decrease lah. Okay, so the word increase or decrease depending on the phenomena that happen in the system. If you energize the system, that means you increase energy stored in the magnetic field. But you de-energize, you remove the energy, that means we decrease the stored field energy. Okay. All right. So this on again the statement represent the relationship between electrical energy, mechanical energy, and also the stored energy in the electromechanical device. So for loss system, I mean if we assume lossless, there is no resistance loss, there is no windage loss, there is no core loss, then we can write the equation of this statement in differential form. We call it differential form, where d omega e dWe equal to dWm plus dWf. So d represent the differential form of energy. The small chain, or the chain, you can say the chain. The chain of electrical energy equal to the chain of mechanical energy plus the chain of stored energy in the magnetic field. So this is very important equation to relate the electromechanical system. D stands for the differential form. Very straightforward lah. So what is d omega e? What is dWe ni? This represent the differential chain in electrical input energy. Okay, equal to I d lambda. Equal to I d lambda. Okay. This one, this one represent the differential chain in the electrical input energy just now lah. Here you got electrical. This is input lah. This is input. So the chain here is called it d omega e lah. Equal to I d lambda. Later we check what is I d lambda. We know already the plot where last time we got plot. This is lambda. This is lambda and this is the current. This relationship between lambda and current. Okay. For any material, represent the relationship between lambda and I given by this one. Right. So d omega WM represent the equal to f dx lah. F mat ds equal to the differential change in mechanical energy output. A small chain or differential chain in mechanical energy represented by dWm, and dWm represent the differential chain in magnetic store energy. Okay. So this present all this part lah. Understand? Straightforward je formula dia. You just put dWe, just here also put dWm and dWf. This stand for the different form or change in the magnetic store energy. Alright. So now we're going to write down further lah. Okay, what is the dWe just now? Is a differential chain in electric energy, can be written as this one lah. You can just put a little bit elaboration. We know the energy equal to power dt. Power equal to REI. E is in this voltage, multiplied by current, multiplied the time taken, equal to P dt. So what E we studied before is in this voltage equal to d lambda by dt, and we can substitute here lah. We can substitute here into E there. Then we can get this equation. So dWe equal to I d lambda. That is relationship between electrical energy and the magnetic store in the magnetic field in the particular system lah. Okay. Then we can substitute. Okay, this one also the same thing lah just now. Okay, this okay. No problem. Okay, that is power. The formula. Hope you can follow the formula here. Now we just go further. What will happen next? All right. Now we go to the energy, co-energy, and force. This is very important formula. So what is energy? What is co-energy? And what is the force? So in any device related to the electromechanical. Okay, to understand more about the energy, co-energy, and force in any particular device, so we study on this simple relay. We can take any device, but here we just follow on this electromagnetic relay based on PCCM book lah. This we just study based on PCCM book that we ask you to check lah. There are many ways to study, and you can refer different book, different method they use. But here we just focus on the method shown or by the PCCM. How they got this relationship between energy stored, and after that from the energy how can we get the torque produced or force produced there lah. Okay, consider the electromagnetic system below like this. This where if we study, we told you before, this immobile part, something that stationary part where we inject the current here. So when you got the coil, you got R represent the losses there for the electrical system. This is a source voltage. This is induced voltage. This is the current flow in the coil. Then you got flux there because you got N there. The source of flux coming from the current. So the flux will flow here and to this one. This is a gap, represent the air gap of the relay. And this is a movable part where when you energize, that means this part will attract this one. The immovable part to the metal there. And when you de-energize, it will open like that. X represent the length or distance between this point and some reference point there. So you got S and G. It's actually same thing. When G change, X also change lah. Simple like that. When you got dG equal to negative dx lah. When G bigger, X smaller like that lah. Okay. When D negative dG got plus dx. Basically same thing. We can represent the energy or the torque later on by using G or X. X is distance from some certain point there. G represent the air gap of the relay ni, and the force produce F. Okay. This is a system that we're going to study detail. Alright. Okay. Just now, mechanical force Fm is actually defined as acting from the relay upon the external mechanical system, and the differential mechanical is given by this one. So basically, when force appears there, the mechanical got some the differential mechanical form ni happen when we force produced by certain distance at lah. That is formula for the energy stored in mechanical lah. Okay, then the same thing lah. It's actually same formula before. So, and what is energy stored here? So when we inject the current there, it's stored energy there, right? The energy stored in that particular relay ni given by this formula. So that means this magnetic energy, differential magnetic energy minus differential in mechanical energy. Formula is come from this one lah. Yeah, this formula. So you just bring there lah. So D omega F equal to D omega E minus D WM, just like that. So differential in magnetic stored energy equal to differential in electrical energy minus differential in mechanical energy, where the differential in mechanical energy is given by formula F dx, F dx formula there. So whenever you got change in x, you have change in the WF and also the WE. All right. So based on equation here, we found that the value of stored energy in magnetic field, this stored energy in magnetic field, is uniquely specified by the values of lambda and x. The two components that cover or control or govern the WF. First lambda, which is flux linkage, d lambda, and the other one is x. X is the length distance just now. Flux linkage somewhere there lah. When you got flux, they got flux linkage. This is flux coming. Flux linkage basically nx and flux equal to lambda, flux linkage. Okay, so two parameter that control energy stored here. First is lambda, the other one is x, distance. So two component lah, two variable that govern or determine the amount of energy stored in the magnetic field. What the component? Lambda and x. Lambda which is flux linkage and x distance just now. Okay. Then, okay, this to show the relationship just now. What is that DWF basically? The chain of magnetic field stored. Basically, we plot the graph just now. This is lambda versus I. Okay. So the both area here represent d lambda, the chain of d lambda, and here the distance from here to here is lambda 1 minus lambda 2 or d lambda, and the shaded area ni represent this one. The chain of small stored energy or the chain of magnetic field energy equal to I d lambda, represented by this one. So if we integrate this one, so we just dWF ni, we integrate that one with the integration of this I d lambda. So this one become WF lah, equal to I lambda. This formula for the energy. So in magnetic field, the magnetic stored energy can be determined by this formula. Okay, this formula represent the magnetic stored in this particular electromechanical device. We just you need to integrate from 0 to lambda. This 0 lambda, integrate I d lambda. So later on we know the formula for what is the equation for I in current. What the current look like? We just substitute there. Integrate with respect to lambda. We can find the energy stored in the magnetic field. Total lah. Ini represent total, the shaded, the whole area ni. Ni represent by using this formula. In order to you need to find the total energy stored, you need to integrate lah I d lambda. Okay. So that's how we. But in this case we need to assume this we say that when we inject the current there, so we hold stationary there lah. So that means mechanical force equal to 0. Then the energy stored equal to this formula just now. I d lambda, integration 0 to lambda, I d lambda. Assume the movable part had stationary, I increase. So because we hold stationary, that means F equal to 0 lah, F max 0. Then we can get this formula. So these are the amount of energy stored in magnetic field lah. When we inject the current, we hold the the plunger just now, or the movable part just, and we find the total amount of energy stored in magnetic field given by I lambda. Okay. Okay, there is relationship between I and lambda. So if we plot the graph more detail, I need the graph between lambda and I lah. So basically lambda I ni depend on the air gap size. You can see there lah. If the air gap size here, the air gap size of our system ni bigger or longer, then we have characteristic like this. Almost linear lah. Linear between lambda and I ni. Relationship between lambda and I ni almost linear if the air gap is bigger. If the air gap is smaller, dia punya relationship become non-linear. It's become non-linear. So you see the plot there. It's become non-linear whenever the size of air gap is smaller. Right? So this is a characteristic or the theory of the relationship between air gap size and a lambda. Okay, so we know the relationship lambda I like that. This is linear, or this like you call it linear, is non-linear. So then, what is energy just now? We know energy equal to this formula. Energy stored in the field equal to this formula. That means we know that. What is the meaning by this one? The integration I d lambda, the red color one. Red color represents integration of I d lambda from 0 to lambda. Zero ni 0 lah, ni start 0. Ni lambda kan, lambda. So you integrate this I d lambda, we got the area here lah. The red color represent the area of this equation, which represent the energy stored in magnetic field. Okay. Whereas the blue color is a complementary, complementary, which is how to get the blue color. It's integration of lambda di. From 0 to I, ni I, current. 0 to I, we integrate from 0 to I, lambda di. We give the W prime F. Prime ni represent, we call it co-energy lah. Co-energy. This energy stored in the magnetic field. This is a co-energy. So both, later on, this energy that we found from this calculation, we can calculate force or torque. We need to find energy first, then you can calculate torque or force. Torque or force. Similar, you can find co-energy area ni, then after that you can find force and torque. Okay? Understand? So this is the difference between energy and co-energy. Energy actually is a real energy stored in the magnetic field. The real one. But the blue color, the co-energy is not real. It's just a method. It's a way or technique to find the energy, the stored, the force later on. So we're going to calculate force. You can use both, either the red color or blue color. But practically the real energy stored is the red color one. The blue color is nothing lah. It's not stored energy. It's just a way to calculate the value of force and torque later on. So that another way, we can use normal one or you can use co-energy one. Okay. So if the system is linear, similar. If the system is linear, the area is similar. That means if the area is linear, then the area should be similar between these two. Okay. So energy, you know already, this formula for energy, I d lambda, integrate from 0 to lambda, and co-energy, this formula lah. Integration from 0 to I lambda di. And remember the prime there. The prime ni represent the co-energy. Dot atas tu, ada dot lah. Dot notation ni represent the co-energy lah. So if you add these two area, you got lambda I. If you add this color and the blue color, red color and blue color, we got back the lambda I, which is the square wave lah. So the square wave ni represent lambda multiplied by I equal to, we add these two part lah. Okay, if the statement here, if the co-energy bigger than energy, then this system is non-linear lah, definitely. If the WF prime equal to WF, this system is linear. So this statement there lah, you can see that statement there. The quantity of co-energy has no physical significance. There is no physical significance. There is no real part. However, it can only be used to derive expression to find the force or torque developed in an electromagnetic system. Okay, so WF priming it's just a method for us in order for us to derive or to calculate the force of torque. It's a technique lah. It's a technique. But in physical one, no, it's nothing there. The physical energy basically is a WF only. Yang ni yang betul. Create the real energy stored in magnetic field is this one lah. This are nothing, just a way only for us to calculate torque and force later on. So we find energy or co-energy. From that we'll calculate the torque or force. Then depending on the system, we have to see the system, whether the system is singly, one wire only, or doubly, two wires, and so on. There are many kind of system we will see later on. Okay, so now we're going to find the torque. We know the energy already. We know the co-energy. So how are we going to the torque or force of that particular things? So we go. Okay, first we see the nonlinear system. In our system we have nonlinear. Nonlinear mean just now lah, lambda I kan, then the currency is nonlinear. This is nonlinear. So how we going to find the energy or find the force from this energy? This, you know, the energy there. How you going to find force from this particular area? Okay. So just now, okay, now we go back to the equation just now. dWf lambda x equal to this stored energy, stored magnetic energy equal to stored or differential in electrical energy minus differential in mechanical energy, where the dWe equal to I d lambda represent the differential change of electrical energy minus the F dx, which is the differential in mechanical energy. Okay, and it has two functions there, lambda and x. Lambda is flat linkage, x distance. Remember, lambda is a flat linkage. When you got flat flow, then you got flat linkage lah, which is m multiplied by pi. X is this distance, this distance between the movable part to a certain reference point to x. Okay. So two parameters that control the energy stored in the magnetic field. Okay. All right. So this equation represents this one. Now, in order to find the torque or force, there are ways to do that in mathematical way lah. They call it the partial derivative lah. For any function of two independent variables, this is a mathematical theorem, I think, where at that function you got two variables, x1, x2, let's say, the total differential form or differential equation of f ni, with respect to the two state x1, x2, can be written as this one. This mathematical function, don't ask me why like that. This is the function that people already prove lah. They do the experiment, they prove that any function that have two unknown variable, for example x1, x2, the total differential equation of that particular f ni, with respect to these two variable, can be written as this one. Ini general formula. So differential of the variable f, function f ni, can be determined by you call it this a partial derivative. Partial derivative of the function with respect to x1. While doing that, x2 must be constant. You got two variables, x1 and x2. When you do get partial derivative for the x1, x2 must be constant. Okay. Plus, while we do the partial derivative for f ni, with respect to x2, x1 must be constant. That is the formula lah. The formula, we just follow the formula only lah. So don't worry, this one won't be asked you in the exam. We just show the flow only. The flow, how to get the equation for force or torque. Okay, so we got this statement. So we can use partial derivative to get the total differential equation for this function. All right. So now we try to relate this one with our original equation, where in our equation we got two variables there, lambda and x. Lambda and x. Function is omega f, wf. Dia punya state variable dia lambda and x. So we just substitute lah lambda and x in our original here. So x1 is lambda lah, is lambda, which is the flat linkage. X, you put x only, the distance. So we just do the same thing, change everything here. S1, S2 change by lambda x, then we can have this one. So the total differential of energy, our function energy, equal to split by 2. So we need to get partial derivative of lambda. While doing that, x must be constant, and then partial derivative of the WF ni. While doing that, lambda must be constant. So to that one. And then we mesh this two equation with the original equation for the energy stored there just now. So when energy stored state that the differential in stored energy equal to I d lambda minus F dx. You just mesh lah. You mesh. What we focus, we want to know is a force. We don't bother about I, we focus about F, force produced there. So the force produced can be obtained by this term. This term. So meaning that in order to find the force, we must do the partial derivative of energy with respect to x. While doing that, lambda must be constant. Very simple. So this formula to get the force in the electromechanical system. So we just focus the second one. The first one we don't bother much lah, because we want to know the mechanical force F. So F can be determined by get the partial derivative of the energy. While doing that, lambda must be constant. You need to do this like different differentiation. You need to do partial derivative. This is differentiation with respect to x, and lambda must be constant while doing that. Okay, this formula to get the force of any electromechanical device. And there's minus there, why later on we explain why minus there. Okay, this is for the non-linear system. This is a formula to get the force from any non-linear system. So this is our system just now, non-linear. This energy, okay, lambda I, this formula lah. So you need to get differentiation of this particular energy. Formula this, you got energy there. So do that one, but you need to do the partial derivative. While doing that, lambda must be constant. Okay, so if the system is linear mean straight lah, straight line. Lambda I linear, okay, I and lambda linear straight, okay. Then okay, we can do something. So little bit change lah, because linear. So I lambda ni, I d lambda can be represented by the equation of this one. You know the slope there. This slope L equal to lambda over I. Remember this formula. So I equal to lambda divided by L. So I equal to lambda divided by L. Then substitute here lah. Substitute here. Then you got lambda over Lx d lambda, because L function of x. L to the inductance dia depend on x. And when x change, because this is the electromechanical system, dia punya time varying lah. When x change, L also change. Then change I to lambda divided by Lx, and then integrate. You need to integrate with respect to lambda. So lambda integrate, got lambda squared over 2 to Lx. And this for energy. Okay, in order to find the force produced, use this formula just now. You know energy. First find energy first. Energy already found for linear system. Then the next step, you need to differentiate using this formula lah. Using formula, you need to differentiate the equation for energy ni using this formula just now. F equal to partial derivative of energy with respect to x, lambda constant. Then substitute here lah. Substitute this formula inside that. Then we got there's some way you need to follow. So 1 over Lx ni jadi Lx negative minus 1. Then do some, they call it double differentiation. You have to do 2 time differentiation. You must do the 2 time differentiation. Then you got this formula. Half I squared dLx per dx. Then you got the force for the particular device. This senangnya. In order to find the force of any particular device later on, relay ke, actuators ke, whatever lah, any magnetic system, whatever, then you can use this formula. Half multiplied by I squared, then multiply dengan dia punya differentiation of the Lx. L ni equation for inductance. Ini inductance lah. When you got the coil just now, you got inductor. I think this we studied before in the previous chapter, inductance. You got self-inductor, mutual inductor, and that is meaning by inductance. So you know the inductance equation. We differentiate in the inductance equation multiply by half I squared, then we got the force. Simple, yeah. Kalau linear lah, kalau system is linear. Then if it's non-linear, you need to do the again. You cannot just substitute like that lah. We need to do some you need to see the equation exactly, what equation for I and so on. But if it's linear, then normally we have this one. So normally in our system, in our study, to make easy lah, everything in linear. Linear mean all the magnetic normally store in all the energy stored in magnetic field. Then everything is easy lah for us. Understand? So force can be determined by half I squared dlx. Okay, this is a force. About the torque, if this system is rotate, that means you need to find torque lah. Torque Newton meter. So just change x to theta only. X ni distance just now. Because they rotates kan, change to theta angle. Then do the same thing lah. Instead of force, pakai torque je lah, ganti. Force ni you change to torque. So torque equal to same formula just now. Okay. Torque equal to pressure derivative of energy with respect to theta. While doing that, lambda must be constant. Then you got the torque formula. The formula for torque. Just change x to theta only. Then we got the same thing lah. Alright, that is how we calculate torque from the energy or force from energy. Now the second part, we need to find the torque or force from using technique co-energy. Just now we done already for the force using energy. We have found the formula equal to what? Formula for the force equal to half I squared differentiate dls over dx. Differentiate inductance with respect to x. Multiply by this term, you got the force. Okay, if the torque, then torque ni T, this one become L theta lah. L theta. Straightforward. If for the torque, you just got torque equal to half I squared dl theta over d theta. Then you got the answer for the torque. So we don't do here lah, but the same thing only. Right. Then okay, if we going to find the force or the torque using co-energy just now. Is co-energy just now? Remember the blue color here? The blue color represent the co-energy. WF prime. Ada prime though. So how you going to find the torque or force from this co-energy concept? Okay, just now we got formula there. So we find the formula for the this formula for the co-energy. This co-energy kan, this is your co-energy. The bottom one lah, bottom one ni, this lambda I, this co-energy lah, this omega. So this one is equal to lambda I minus energy. This part, the red color just now, the left side is energy. So the square ni, I lambda minus the energy on the left side ni, dapat you got the WF prime, which is co-energy. Okay. But remember, for the co-energy, with respect to Ix, I and X, not lambda, I and X. Previously lambda and X, because this one represents this side, the right side is I, the current. Okay. For the energy, lambda X. For the co-energy, Ix. This one, Ix. Then, okay, you just put D there lah. You put D in differential form. In differential form, just put d lambda dwf prime Ix equal to d I lambda minus d wf lambda x. Okay. And then this one, we know already before. This is the magnetic stored energy. Magnetic stored energy equal to electrical energy minus differential electrical energy minus mechanical energy. Substitute there. Substitute in this part. With this one. And then d I lambda ni, we can, because there are two different variable, we can, actually it's a I d lambda plus lambda di. It's expanding there, expanding kan dia. Then substitute all this to the original equation. Yeah, you can have this one. Okay. So the differential in co-energy equal to lambda di plus f at dx. So what we're interested now, F force ni, force. Then you do matching again. We do matching again using the technique we studied just now. This technique. this technique, partial derivative technique, when you have two unknown variable, the total differential can be determined by this technique. So now just change lah. Instead of using lambda I, now we pakai apa? Ix, two different I and X, because it is a co-energy. So got the same thing there. And just do it, just repeat what we have done before. Okay, then we have this one. Okay, so for the nonlinear system of the differential equation for the Wf prime Ix equal to this one, partial derivative of co-energy with respect to I. By doing that, X must be constant, plus partial derivative of Wf prime with respect to X. While doing that, I constant. Then what we're interested is force. You just mesh this equation with this equation, then here you see the arrow there lah. So force is represented by this one. In order to find the force using co-energy, we can have the force using this derivative of partial derivative of co-energy with respect to X. I must be constant. When you differentiate X ni kan, energy with respect to X, the current must be constant. Then you can find force there. Simple lah, just follow that. Okay, matching. So by matching that part, we know that the force given by this one. Lambda also can find lah, but we don't interested on lambda. Lambda also can find by this part, but we're interested on F only, force. So force can be determined, mechanical force can be determined by partial derivative of the co-energy with respect to X. Why doing that? Current must be constant. Okay. So that's how we calculate or find the force from the electromechanical device. We can use two ways. First, by using energy. The second one by doing energy. So this is for non-linear. If system is linear, then we can do the same thing lah. Just put co-energy lambda di. Remember formula dia? Lambda di. So you must remember there's two formula that involved. Go back here. Co-energy lambda di. You have this one formula. Lambda di integration from 0 to I lambda di. Yang ni energy integration 0 lambda I di lambda. So student sometimes confused there lah. They get problem here. Sometimes they mix different formula. You need to be firm there lah. Energy using this one, co-energy using this one. Okay. So I lambda di to find the co-energy. Go back here. Lambda di lambda di, and because the system linear, you just change lambda equal to Lxi, formula dia. It's linear, so formula lambda can be changed directly. Then integrate I, integration of I, so got I squared over 2 Lx. Okay, this is energy, co-energy. Then after that, we use the formula just now we found here just now, this one, F force. Jadi in order to find force, we need to differentiate the co-energy. Then you got this formula. So sama kan, same. You can see here, the force obtained from the energy, co-energy equal to half I squared dl per dx. The force obtained from the energy of same formula. Just now you got the same thing, right? Same thing. Same. See, just now everything similar. Okay, the same. I already. So half I dlx per dx for the energy method, and with the co-energy we got the same thing, half I squared dlx per dx. Similar thing. Okay, so what is the conclusion now? So both method can be used in order to find the torque of force. We can use either the energy method or you can use the co-energy method. You got the same force. Alright, I think that's all for today. So we will continue more on next lecture, and we'll do some example to explain this thing, and I will elaborate more on the what actually plus minus there lah. Here you got plus, but here you got plus sign there, right? And here you got minus sign, why like that? So we'll explain more on the next lecture lah. Anything that you want to ask? Stop. All right. Anything you want to not very clear here? What you can ask now? Remember this one, Remember this. This one you need to remember this one, lambda I relationship, which one energy, which one co-energy, the equation involved. Okay. The process that I showed just now is not asked in the exam. And this one, for example, nothing. What you got to do, you use formula only. Okay, you need to use formula only. For example, to find the force, use this formula: half I squared dlx per dx. To find the torque, half I squared dl theta over theta. Okay, that's only you need to know to use. So the rest, the derivation, normally we didn't ask you to get how to get the force equation and so on. What you need to do, use this formula and calculate all the problem given to you. All right. Okay. So I try share back in the attendance. So today finish. So later on we meet you again on next week lah. Next week, Monday is a holiday. So we meet you again at the same time online again next week. Okay. So the class last missed 2 hours lecture next week. We see later on lah. If we manage to cope the subject, we don't need to replace lah. Otherwise, we do online class later on. We do class later on. I try to get back the attendance. Where is it, the attendance just now? It's very difficult. I don't know why. Attendance. Always like that. Something went wrong. Remember, I share the QR code here. I already snapped the QR code just now. Still okay. Something went wrong. I don't know whether you can scan or not. I try. Because resistance got problem now. Okay. Okay, I share to QR code in the WhatsApp. Here